So kinds of reaction, this is a lot of, hopefully is review. Substitution reaction, just like it sounds. You're substituting one atom for another atom. Basic level substitution. We're not talking about SN1 or SN2 yet, just substitution. That's a substitution reaction. An elimination reaction. You eliminate something, right? So an elimination reaction, you actually you always make a pi bond. In elimination, you always make a pi bond. You eliminate two things. A single reactant splits into two products, right? You eliminate two things. Two groups are eliminated from a starting material, and it always makes a pi bond. That's an elimination reaction. An addition reaction is just the opposite of an elimination reaction. Elimination reaction gets rid of two things. An addition reaction adds two things. All right, adds two things. We're not worrying about the mechanism yet. A rearrangement is a single reactant undergoes reorganization of its atoms and bonds to yield a single product that is an isomer of the original. All this means is the arrangement of these atoms are moving. The bonds don't change. All the bonds are the same. The bonds just rearranged. So if you have 5 sigma bonds and 5 pi bonds, and you rearrange, the product's going to have 5 sigma bonds and 5 pi bonds. That's a rearrangement reaction. Easy. Bonds can break two ways. Homolytically, one electron at a time, or heterolytically. This is what we're going to focus on right now. 2 electrons moving at a time, the double-headed arrow. Bond formation, right? Again, we're going to focus on the hetero bond formation. Lone pair is moving, double-headed arrow. Not worried about this so much. Electrophile is electron deficient. Nucleophile is electron rich. One-step mechanism has one hill, one transition state, one step. Right? This is a delta G, all that kind of stuff. I don't emphasize that, but I'd like to think you have a working knowledge of free energy diagrams. We'll hit them more. But one step means one transition state. 2 steps means 2 transition states, and you have an intermediate. Right? So transition states are steps. The hills, the tops of the hills, tells you how many steps you have. Nucleophile versus electrophile. Nucleophile, lover of the nucleus. What's the charge of the nucleus? Positive, because it has protons. Nucleophiles love plus charges. Opposites attract. Nucleophiles are electron rich. All Lewis bases, which by definition are electron rich, are nucleophiles. So a bunch of examples. Things with lone pairs, negative charge. Those are nucleophiles. Pi bonds can be nucleophiles. Electrophiles, lover of electrons. Electrophiles are electron deficient. All Lewis acids are electrophiles. Right? Examples of electrophiles, alkyl halides, electron deficient atoms, of positively charged species. Classic example, I always like to bring it up. Hydronium. Where is this electron deficient at? Is it electron deficient at the oxygen, or is electron deficient at the hydrogen? Where is the electrophile? Which atom's electrophilic? H or oxygen? Which one is it?
But wouldn't it be...
Forgot to draw the lone pairs in. That's important. This helps you know, just because something has a plus charge doesn't mean it's electron deficient. The hydrogens are the electrophiles here because an OH bond is polar. Lewis dot structures lie to you sometimes. You got to stop and think about what's going on here, right? So this is where it's electron deficient at. Some more basic examples just in form. A carbanion, a carbon bonded to a metal, is going to be a nucleophile. That's a C minus. An oxygen here with lone pairs, a pi bond can be a nucleophile. Electrophiles are anything a carbon bonded to an electrophilic, an electronegative atom is really delta plus. Carbocations, right? Literally a cation plus charge. Or boron or aluminum, things that don't have a full octet, right? This doesn't have a full octet. Even though it doesn't have a charge, it doesn't have a full octet, right? So that's a good electrophile. This is like a classic Lewis acid. Okay, last pit. What are the kind of steps for nucleophile? Like what kind of arrow pushings are there? And I would never ask you a question that says, hey, draw me a single step nucleophilic attack, right? I think these are just being named so you can kind of an anchor of what kind of things to expect. A lot of times these steps will be added together, right? But these are the kind of basic movements. Single step, nucleophilic attack, nucleophile, electrophile. Forms a new bond. Two-step nucleophilic attack. Addition, adds in, elimination. Right? So this is really like two steps. This is an addition reaction. And then the next step, when you form that pi bond, it comes down. That's a elimination. But the two steps here is adding in two arrows. Two-step nucleophilic attack gets to this. Notice how this is incorrect, because of course carbon wants to have how many bonds? 4 bonds. Good. Loss of leaving group, just leaves. Bond breaks. Polar bond, bromine's like, I'm out of here. I'm electronegative. I want these electrons. Proton transfer, this is where I gave it away before, right? Again, here's that H2O plus. Where is it electron deficient? It's electron deficient at the hydrogen, right? At the hydrogen. So a lone pair here could take it, or a negative charge. That's just moving a hydrogen around. That's called a proton transfer. Other examples, I kind of hit on before. A Bronsted-Lowry acid is a Lewis acid that deals with hydrogen. All right? Same with Bronsted base. It's a Lewis base that just grabs a hydrogen. So let's just focus on the hydrogen part. Right? Acid base, conjugate acid. Right? Those are the kind of things that are going on. Acid-base mechanism, you all would know this already. The electrons start at the electron-rich species, which would be the nucleophile, which would be the base always. Right? And if you're not sure, just look at the bonds, broken bonds formed, and I'll tell you where to draw the arrows. The arrows show the movement of electrons. It shows you which new bonds are being formed. Each arrow has 2 electrons. How many electrons in a bond? Gives it away. And then Lewis acid, Lewis base reactions. A lot of times they're more simpler. But again, these are things you see. This looks like an SN2 reaction to me, right? This is just a Lewis acid, Lewis base. The boron doesn't have a full octet. This lone pair goes here. We get a minus charge on the boron because it got electrons, plus charge on the oxygen. And this is just like an SN2 reaction.